This is my sixth video lesson for Unit 9. In this lesson, we'll learn how to calculate the half-life of a radioisotope. Go to page 25 in the class packet. Learning target. At the end of the lesson, I'll be able to calculate the half-life of a radioisotope and the age of a substance. Won't be number 6, which will be a doing a pod based off this lesson. In the previous PowerPoints, we have been talking about radioactive decay. In this lesson, we'll be talking about how quickly does radioactive decay happens. Half-life is the amount of time it takes for half of a radioisotope to decay. It is a chemical property of an isotope. The half-life is listed on Table N for the radioisotopes. We're now going to do a simulation on half-life. Take a moment to cut a strip of paper that's 8 inches long. In this simulation, the strip of paper represents a radioisotope. Every half-life, half of the radioisotope will decay. We will be demonstrating this by ripping the paper in half after each half-life. The half-life of the strip of paper is 2 seconds, so every 2 seconds, we'll be ripping the strip of paper in half. We'll be graphing the simulation as well. On the y-axis is the percentage of the paper remaining. On the x-axis is the number of half-lives that's passed. In the beginning, we have 100% of our radioisotope, which is the paper, which is 8 inches long. In the graph, it will be this point. After the first half-life, half of the radioisotope has decayed. Therefore, there's 50% of the radioisotope that's left over that has not decayed yet. The fraction of 50% is 1/2. A half of 8 inches is 4 inches. This means we still have 4 inches of the paper that is radioactive. On the graph, we're going to plot it here. If another half-life occurs, half of the remaining radioisotope will decay. So half of 50% is 25%, which is 1/4. This means 1/4 of the substance is still radioactive. 1/2 of 4 is 2. 2 is 1/4 of 8. So 2 inches of the paper is still radioactive. If we were to graph this point, it will be over here. When another half-life occurs, half of the remaining radioisotope will decay by half. So half of 25 is 12.5, which is 1/8. This means we still have 1/8 of our substance that is still radioactive. Half of 2 is 1, so 1 inch of our paper is still radioactive. To graph this data point at half-life 3, it will be over here. For the fourth half-life, the percentage will be 6.25, the fraction will be 1/16, and we have 0.5 inches of paper that's still radioactive. The fourth half-life data point will be here. This represents an example of a graph about half-life, which is exponential decay. On the regions, make sure you know how to read a graph like this. Here's another picture about a graph about half-life. The red atoms represents the parent radioisotope. When it decays, it produces the daughter isotope. With each half-life, half of the parent isotope becomes the daughter isotope. Let's review the simulation. What does the paper represent? The paper represents a radioisotope. The amount of time it takes to rip the paper in half is analogous to the half-life. How can knowing the half-life be useful in figuring out the age of substance? We can use the half-life to calculate backwards the ages of substances. Learning check number 1. As a sample of radioisotope I-131 decays, a half-life does what? Pause the video and resume once completed. The answer is choice 3 because half-life is a chemical property. If we look on table N, I-131 has a half-life of 8 days. Every sample of I-31 will have 8 days as the half-life. When I-131 decays, it undergoes beta minus decay, so it's no longer I-131. In the second half of the lesson, we'll be doing calculations involving the half-life. Here are 2 equations related to half-life. The first one calculates the fraction remaining. The uppercase T is half-life, The lowercase t is the total time elapsed. The second equation calculates the number of half-lives. Keep in mind, both of these equations are not on the reference table, so I'll show you another way of solving problems involving half-life. You should know that the number of half-lives is equal to the total time over the half-life. You have to memorize this equation. The half-life can be found on table N in your reference table. I'll show you two methods involving this equation. The first method is the sequence method. In the beginning, you start off with 100% or 1/1 of your radioisotope. After the first half-life, half of the radioisotope has decayed. So what you're left with is 50% or 1/2 of your isotope that's still radioactive. In the second half-life, half of the radioisotope will decay. Therefore, you have 1/4 or 25% of your radioisotope left. In the third half-life, another half will decay, and you're left with 1/8 or 12.5% of your radioisotope. In the fourth half-life, another half will decay, and you're left with 1/16 or 6.25% of your radioisotope. Keep in mind, the radioisotope will continue to decay with new half-lives. The total time is from the beginning to the last half-life of your radioisotope. The sequence method involves using this diagram to figure out the fraction or the number of half-life or the total time in the problem. The other method is the chart method. Here's an example of the chart. You start off with 0 half-life at 100%. After each half-life, you decrease by half. The chart method is another representation on how to solve half-life questions. I'll show you how to use both the sequence method and the chart method in this lesson. So there's 4 scenarios that you must be able to do for the regions. The first scenario is fraction remaining. You can use this equation. Fraction remaining is equal to 1/2 to the power of total time over half-life. I'll also show you the sequence method and the chart method. Question 1. What fraction of sample of P32 will be left after 42.9 days? Step 1. Find the half-life. For P32, you have to look on table N on your reference table. It is 14.28 days. Step 2. Figure out how many half-life. You have to use this equation. Number half-life is equal to total time over half-life. The total time is 42.9 days. The half-life is 14.28 days. So the number half-life is 3. Next, we plug into this equation. 1/2 to the third power is 1/8. 1/8 will be the fraction remaining of P32. If you want to use the chart method, you still have to use this equation. Number half-life equal to total time over half-life. Then you write the table. You start off with 0 half-life. Then you find the fraction of the third half-life by dividing by 2. You can also solve this using the sequence method. In the first half-life, you go from 1 to 1/2. In the second half-life, you go from half to fourth. In the third half-life, you go from fourth to eighth. As you can see, each of the method will give you the correct answer. Question 2. What fraction of the sample H3 will be left after 49.04 years? The first step is to look up the half-life of H3 on table N of your reference table. It is 12.31 years. The next step is to plug into the equation. Number half-life is equal to total time over half-life. So 49.04 over 12.31 is 4. That's the number of half-life. Next, you can either use the chart method or the sequence method. If you use the chart method, you have to draw the chart and start at 0 half-life and figure out the fraction at the fourth half-life. As you can see, it is 1/16. If you use the sequence method, in the first half-life, you go from 1 to 1/2. In the second half-life, you go from half to fourth. In the third half-life, you go from fourth to eighth. In the fourth half-life, you go from eighth to 16th. So the final answer is 1 over 16 for the fraction remaining. Learning check number 2. Which radioisotope have the same decay mode and have half-lives greater than 1 hour? Pause the video and resume once you complete it. So you have to use table N to look up the radioisotope. The answer is choice 3. Learning check number 3. Based on reference table N, what fraction of radioactive SR90 sample will remain unchanged after 56.2 years? Pause the video and resume once completed. The answer is choice 2, 1/4. Based on table N, the number of half-lives is 2. Using the sequence method, you can see that the fraction remaining is 1/4. Learning check number 4. A radioactive isotope has a half-life of 2.5 years. Which fraction of the original mass remains unchanged after 10 years? Pause the video and resume once completed. The first step is to figure out the number of half-lives, which is 10 divided by 2.5, which is 4. Using the sequence method, every 2.5 years, half of it decays. So after 10 years, you have 1 over 16 left over. So the answer is choice 4. Now try to do the rest of scenario A, questions 3 to 6 on your own. Resume the video once you complete it. Here are the answers. For the next scenario, scenario B, we'll be calculating what is the half-life of the radioisotope. Question 1. After 32 days, 5 milligrams of the 80 milligram sample of the radioisotope remains unchanged. What is the half-life of this element? I will solve this question using the table method. In the beginning, we have 80 milligrams of the radioactive isotope. I would decrease the mass of the radioisotope by half until I reach 5. So the first half-life, I'll have 40. Second, I'll have 20. Third, I'll have 10. Fourth, I'll have 5. So it took the radioisotope 4 half-lives to decay from 80 milligrams to 5 milligrams. From 0 to 4 half-life periods represent the total time, which is 32 days. Next, we're going to plug into the equation to solve for the half-life of this element. We know the number of half-life is 4. The total time is 32 days. We plug it in and we solve for a half-life, which is 8 days. This is the half-life of this element. Try to do questions 2 and 3 in scenario B on your own. Pause the video and resume once completed. Here are the answers. Scenario C involves calculating the mass of the original radioisotope before it decayed. Let's look at question 1. If 12.5 grams of original sample of cesium-137 remains after 90.69 years, what is the mass of the original sample? The first step is to look up the half-life of cesium-137, which is 30.2 years. The next step is to figure out the number of half-life periods that has passed. The total time is 90.69 years. The half-life is 30.2 years. So the number of half-life is 3. So at the third half-life, we have 12.5 grams of our sample left over. So to figure out the original mass, we're going to work backwards by multiplying by 2. So the second half-life, there will be 25 grams. The first half-life, there was 50 grams, and the original mass was 100 grams. So the answer is 100 grams. Try to do questions 2 and 3 of scenario 3 on your own. Resume the video once you complete it. Here are the answers. In the last scenario, scenario D, we'll be calculating how long, how much time, or what is the total time. Let's look at question 1. How long would it take for 50% of the sample of I-131 to decay? The first step is to look up the half-life of I-31 in Table N in your reference table. It is 8.021 days. We'll be using this table to figure out the number of half-lives that has passed. We know in the beginning we have 100%. In the first half-life, we have 50%. Therefore, we know that only one half-life has passed. Next, we plug into this equation. Number of half-lives is equal to total time over half-life. We'll be solving for total time. The number of half-life is 1. The half-life is 8.021 days. So the total time is 8.021 days. Question 2. How long would it take for 30 grams of Rn-222 to decay to 7.5 grams? The first step is to look up the half-life of Rn-222, which is 3.823 days. The next step is to use this table to figure out the number of half-lives. In the beginning, you have 30 grams. We are going to decrease the 30 grams by half until we reach 7.5. So the first half-life, we have 15, and the second half-life, we have 7.5. So the number of half-lives must be 2. Next, we can plug into this equation to solve for total time. So the total time is 7.6 days. Try to do questions 3 and 4 on your own. Pause the video and resume when it's completed. Here are the answers. This concludes the video lesson. Remember to do the Junior Pod homework.